Because what we saw is a lot of teams, took many months, even years, to start a project and eventually get these models into production. So we're sort of in the typical AWS fashion, trying to take away the undifferentiated heavy lifting that's involved in managing these projects. So if we look at the different phases, in a typical machine learning project, we typically have the build, train, and deploy phase. And we'll kind of look at the specific features that Amazon SageMaker can provide that can benefit developers and data scientists. So in the build phase, we have pre-built notebooks. So we give you managed notebook instances with the popular Jupyter open source software, plus a bunch of pre-built notebooks that can solve many different common problems that customers have. Comes with built-in algorithms, so especially for developers who are maybe just starting off with machine learning, not confident to sort of build their own models. We have a bunch of sort of the most popular algorithms used in machine learning that makes it very quickly to get started. We also, if you are using TensorFlow or MXNet, you can essentially just bring your code, and SageMaker makes it very easy to train and deploy those popular open source frameworks. Or even if you have your own custom framework, and this is the focus of this talk, things like PyTorch or Cafe2, you can essentially, by building Docker containers to build and train your models and then deploy them. So in training, we make it very easy to essentially have data scientists have access to infrastructure needed to run your training jobs. Essentially, one-click training is the objective. So SageMaker essentially manages configuring and deploying all of the infrastructure needed to run your training jobs. So this could be a single instance or even a cluster, sort of depending on the size of the task at hand. Another feature is hyperparameter optimization. So often, when you're training your models, there's a lot of parameters to configure, and it's hard to figure out, the right combination of those parameters. So there's a service to essentially find the optimum parameter, increase the accuracy of your models. So then once you've trained your model, we make it easy to then deploy into production. So again, through one click, so Amazon SageMaker will manage the infrastructure and follows a lot of the AWS best practices using things like auto-scaling to ensure that your endpoint that your customers are calling for your machine model inference is highly available, scalable. And also, you can do things such as include A/B testing, so sort of following DevOps best practices in your project. So if we look at Amazon SageMaker, it's actually not one service, it's actually a combination of 4 independent components. Now these components can be used together or separately, so we provide data scientists and developers a lot of flexibility in how they use the service. So we have the notebook instances, so that's where a lot of data scientists will start, so to sort of do the exploratory data analysis. We have a lot of the built-in algorithms to really help you get kick-started with machine learning. The machine learning service for training your models. And then the hosting service where you can deploy and provide an API, say, to your customers or sort of downstream services. So if we go into each one of these, the SageMaker Notebook instances, effectively just think of it like an EC2 instance that we provision on your behalf. This EC2 instance can have a GPU or not, depending on the compute power that you need. This EC2 instance has an EBS volume attached to it, 5 gigabytes in size. And essentially, we put the Jupyter open source software installed on that and give you an endpoint that you can provide to data scientists so they can immediately start doing their data exploratory analysis. Also on the notebook instances, there's a bunch of pre-built example notebooks. So it's essentially showing you how you can, for example, create a recommendations engine. Many of these use cases you can see on the right-hand side, using the pre-built algorithms, using TensorFlow, MXNet, or even giving examples of how you can bring your own algorithm to the platform. So SageMaker has a bunch of built-in algorithms, and essentially there's kind of 3 ways you can bring algorithms to the platform. As I mentioned, we have the built-in algorithms. These are the Amazon-provided algorithms where we essentially manage them. And effectively, we've sort of looked and asked our customers what are the most popular algorithms they're using. And we've made them very performant and able to work on very large data sets. So things such as matrix factorization, regression, k-means clustering, and many more. And recently we actually launched a new one for anomaly detection. And we'll continue, based on customer feedback, increase the number of algorithms we provide. So as I mentioned earlier, if you have MXNet or TensorFlow scripts that you're using, you can bring them. We manage the actual containers for running those algorithms. So essentially, you can just bring your pre-built scripts and they'll work fine. You can bring your own algorithms. This is where there's a little bit more work to do. You have to essentially build a Docker image for your training job and for inference, but it provides the flexibility, right? Maximum flexibility and control that many experienced data scientists have. There's also interworking with Spark. So essentially what we're seeing customers do is they are doing a lot of their data pre-processing in their Spark cluster and then offloading the model training to SageMaker. So if we look at the machine learning training service, the foundational building block essentially is Docker. So I kind of alluded to it earlier. If you're using the built-in algorithms or if you're using MXNet or TensorFlow, essentially the SageMaker team sort of manages and maintains the Docker images for you, so you don't need to do that yourself. And then if you bring your own framework, then that's something that you'll need to do and essentially upload those Docker images into Amazon ECR. So the way the training flow works, it all starts with the training data. So your training data needs to be hosted into S3. But the way the training flow works is that Amazon SageMaker, the training service, will pull the training data into the training component. Depending on what algorithm you're using, if it's a built-in algorithm or your own algorithm, that will determine the Docker image that it will pull into the service. It will spin up the infrastructure needed to train your particular model. And at the end of it, it'll generate a model artifact. So this is typically, say if it's a neural network, all of the weights of the neurons, and save them in some sort of format. Typically a zip file. So then SageMaker, once it has the model artifacts that save locally, it will then upload those model artifacts up into S3. So that's sort of in a nutshell how the training service works. And then for hosting, again, it's building on the foundations of using Docker. Now, it could be the same Docker image, or you can even have a separate inference algorithm, because the compute requirements could be different, the infrastructure could be different for running your inference algorithm. So again, we start with the model artifacts. So this could be the model artifact generated from the SageMaker training service, or you could even train on-premise or use some other, just a standalone EC2 instance to train your model. So as long as you have a model artifact that's zipped, it's put up into S3, that's the only requirement. So the model artifact is pulled into the hosting service from SageMaker. SageMaker will then spin up the hosting infrastructure using the inference algorithm that you decide. So again, this could be the managed one if you're using a built-in algorithm, or your own custom inference Docker image, to then create essentially the endpoint. So this is the endpoint as an API that you give to your end users. So one important part of the inference algorithm is that it needs to support a RESTful interface. So this is essentially where the predictions, the data for predictions will be submitted to. And we'll go into a bit more detail in terms of the requirements you need to build into the inference Docker image. So on the hosting service, as I alluded to earlier, one of the cool features allows you to do A/B testing. So it allows you to have multiple versions of your model for a single endpoint. And then gradually, as you see the performance of new versions of your model, you can shift traffic more and more to those newer versions. So just an example here. So say we have, this is version 1 of our model deployed to an endpoint. We can decide that obviously 100% of the traffic is going to it. And then say we come up with a new idea, a new sort of algorithm for our model. So we can deploy that, and then we can give it a weight. So we can say, initially say 20% of our traffic is going to go to the new model, but the majority, 80%, is going to our original model. So then you can assess the performance of both of the models, say against some ground truth, and then gradually decide how you want to shift your traffic if the new model is performing as it's expected to. All right, so that's kind of just the overview of the SageMaker service. Now we're kind of going to jump into how you can actually bring custom models. That's not part of the sort of the built-in algorithms that we have in SageMaker that you might have seen in some of the other sessions, or the MXNet or TensorFlow. And I'm going to do this through an example. So the example we're going to do is we're going to actually only use 2 of the components of SageMaker. We're going to actually spin up a notebook instance. So the notebook instance is going to actually be where we're going to build and train our model. Because often, many companies don't have massive data sets, right? Could be megabytes or gigabytes. So often, notebook instances is enough and allows you to a lot of iterative development and experiment with training your models. So once we've built and trained a model and we're kind of satisfied with its performance, we're going to upload that into S3, and then we can use the ML hosting service to then deploy this model into production. So the example that library I'm going to go through is Fast.ai. Who's familiar with Fast.ai? Okay, so a few hands, majority are not. So this is a fairly new library. It's based off a very popular online course. So if you're interested in getting into deep learning and have some development skills, I highly recommend checking out the Fast.ai online course. It can really get you up to speed in just a matter of weeks. You can run some of the latest state-of-the-art algorithms around deep learning. So this is a library built on PyTorch. If you've heard of PyTorch, this is an open source library developed by Facebook. And it's really focusing on, so PyTorch is kind of designed for researchers, and Fast.ai is more designed for practical use, so in real world usage. And they have a motto, making neural nets uncool again. So what they mean by that, it's, they want it to be used for, they're not so fancy. It's not trying to solve Go, beating Go players or automated driving, real practical use cases for machine learning and deep learning, which often for a lot of companies is actually the most value. If you think companies have a lot of data sitting in data warehouses, what should we call structured data, so it's really ideal for those sort of data types and practical applications. So Fast.ai works really well with AWS. This is just a screenshot of a recent sort of benchmarking study that they did, where it was essentially a bake-off and assessing different teams, seeing who can train essentially the models the fastest, and also at the lowest cost. So a team took the Fast.ai library using AWS, sort of standard infrastructure, and managed to, beat a lot of other teams that had, custom hardware, really optimized, deep research teams. So it's just kind of showing the sort of the power of this library, combined with AWS is a really good, nice solution. So the example that we're going to go through, I'm not sure if you're familiar with Kaggle. This is a fairly sort of rudimentary sort of example of computer vision, so image classification. So the example we're going to go through is that by giving an image, it's going to detect if it's a dog or a cat. So not the most fancy, but just to kind of prove the example of how these things can work together. So this is in sort of an open data set that we're going to be using in the example. So how the example is going to work is we're going to spin up a SageMaker Notebook. We're going to be using the GPU-based notebook because we're actually going to be training our deep learning model. So the model is a convolutional network, which is essentially the state of the art for computer vision image classification. So we're going to run through the code there. We're going to upload. So once we've trained our model on the notebook instance, the model artifacts are going to be uploaded, they're zipped and uploaded up into S3. So that's kind of our build and train phase. So now, because we are using our own algorithm, none of the sort of off-the-shelf or built-in algorithms as part of the SageMaker service, we're going to have to actually build our own inference Docker image. And we're actually going to use Cloud9. So Cloud9 is the hosted IDE from Amazon that we launched the end of last year. And the nice thing about it is it provides a nice coding environment and includes Docker, so we can basically build our images on Cloud9 and then push them up into Amazon, our private Docker repository. So once we've built and pushed our image, then we're ready to host the model on the SageMaker hosting service. So the SageMaker hosting service essentially just needs two things. It just needs those model artifacts that we built earlier and pushed to S3. And then the inference image, and it's ready to deploy. The other thing we're doing is that, I mentioned earlier, on the notebook instance, we're using a GPU-based. But often, even for deep learning, you don't actually need a GPU when you're actually deploying your code to production for inference. Often the compute-optimized Intel C5 or C4 instances work really well and often have a lower running cost than the GPU-based instances. So that's them all together. So just a couple of words on building your inference Docker images. So there's a few things that you need to be aware of if you're building your own inference image. First of all, you have to understand how Amazon SageMaker calls the Docker image when it's actually running them in production. So it's basically running this Docker run command. You give it the name, so the reference of your Docker image in the private repository in Amazon ECR. And Amazon SageMaker will also pass in the parameter serve, so you have to sort of be aware of that and sort of configure your entry point to your Docker image to handle that command. The other part is understanding how you're going to access the model artifacts. So these are the saved parameters, say, of your neural network. So the good thing about SageMaker is it handles the copying of your artifacts from S3 into your local running Docker image. So where you have to look for the model artifacts is not in S3, but you just need to look in a mounted volume in your Docker container, which is opt.ml model. That's where you'll basically pick up that zip model so you can then load your model into memory. Also, how the inference image is accessed from the endpoint. It's also important to understand this. So you have to have essentially a REST-compliant web server running in your inference image. And there's two APIs that you need to implement in that web server. So the first is a /invocations path. So this is where essentially the data that you want to do a prediction on gets posted to. So in our example, we are doing an image classification. So the actual data will be the raw image. So the JPEG image itself will get posted to that endpoint in a HTTP post request. So if it's if you're doing things like structured data, it could be a CSV file or a JSON file. And what we're going to get back is a JSON file, giving the class of what it's predicting the image to be and a confidence score. So the other path you have to implement is the ping API. So SageMaker will frequently ping your endpoint to check the health of it, make sure it's healthy. So you need to implement a /ping reference path with a get, and then return 200 success if your inference server is healthy. So now, getting into how you actually bundle the code together. Good practice, because a lot of the machine learning libraries are implemented in Python. We generally recommend to bundle in Nginx as a reverse proxy with Gunicorn and then Flask. So Flask is a very popular RESTful framework for Python applications. So this is a good combination to use. Alrighty, so now we're going to jump into the demo. So let me just switch here. can see that right. So this is just showing the main SageMaker console, web console. So showing the 4 separate components. So showing the notebook instance, the jobs, models, and endpoints. So what we're going to do is we're going to essentially fire up our notebook instance. Now, when you fire up your notebook instances, it has a bunch of what we call Conda environments. So Conda environments is essentially defines a specific version of Python, as well as all of the libraries and dependencies for the particular libraries. So you can have multiple Conda environments running on the same instance with different versions of Python and different versions of the dependent libraries and packages. So one of the things to note about since we're using Fast.ai, thankfully, and we'll have a look here in the, let me just open it here. So this is the, hopefully you can see that okay. This is the Fast.ai library on GitHub. So Fast.ai is an open source library. And the good thing about it is that it actually has a Conda environment defined here. So this is the environment.yaml file. So this defines essentially all of the Python packages and other dependencies that the Fast.ai library needs to essentially run. So it'll be, because it's built on PyTorch, you can see up the top there, it has the dependency on PyTorch and other packages. So essentially what we need to do, first of all, is set up the Conda environment for Fast.ai on our notebook instance. Now, one of the things on SageMaker Notebook instances is that when you stop and start your notebook instance, those custom libraries are not saved. We got the feedback from customers that this was not a pleasant experience. They would have to manually run commands on the notebook instance. So we introduced a new feature a few weeks ago called lifestyle configurations. So if we just go back to the console here and go back into our notebook, you can see this new, if you haven't been in the console for a while, you will see this as a new option in the lifestyle configurations. So what a lifestyle configuration is it allows you to define some scripts that will be run both when your notebook is created, the first time it's created, and then every time your notebook is started. So if you want to install custom libraries, you can essentially just call conda create environment in that lifestyle configuration script, and it will automatically set up and have your notebook instance ready to go. So we have one pre-configured here. So here we have 2 scripts. So we have one script when the notebook instance is created. So this is doing things such as we're downloading the training data onto the EBS volume. We're also installing the Fast.ai library and also installing the demo code for this, application. So that's when it started. So the EBS volume itself is saved, but not the custom libraries and the Anaconda libraries. So that's what we need to do is we need to, in the start notebook script, this is where we need to set up our environment. Especially because we're using a GPU instance for our notebook, we don't want to have this running unnecessarily. So we want to stop it. For example, when the data scientist goes home. So in this particular script, when the data scientist comes back in the next day to continue their work, it'll install all those libraries for them. So then here we've just got the conda env create update commands, which will install essentially all of those packages for the Fast.ai library. Cool. So we've gone into lifestyle configurations. So creating a notebook is fairly simple. We just go into the console here. We'll give it a name. Here is where we choose the instance type. Because we're training our model on the notebook instance, we actually want to choose a GPU-based. So this is a fairly new option as well. Before there were only a couple of different instance options. Now we're supporting most of the EC2 instance types here. So we can choose the P3 which has the very latest NVIDIA Volta V100 GPU there. So it really accelerates our training of our models. We can choose the VPC. And here is where we define the lifestyle configuration. So this is the scripts that I just showed you earlier. So we'll install, download the training data and install the Fastai libraries. So this is going to take, more than 10 minutes to do because there's quite a few libraries in here. So I'm not going to actually do this. And like every good cooking show, I have one pre-prepared. So this is the Summit Training Notebook here. You can see it's in service. So once that's in service, it's really easy. You just need to basically click here, open, and this is going to open up the web console for the Jupyter application. So here's my application. So this is something that was set up through those scripts. So we can see here we have a data directory. So our lifestyle configuration on create script has set up our data here. So we can have a look here. Here's our dogs and cats data. It's going to be quite slow because there's quite a few files in there. I might just create a new one because it's probably blocked up a bit. Oh. Joys of demos, huh? Right. I might switch to one of the other console. Hold on a sec. So let's try this one. Okay. Okay, so we've got our data directory. We also have, these are the sample notebooks. So, if you want to get familiar with the built-in algorithms, knowing how to run TensorFlow or MXNet, there's a lot of examples here that you can go through. Whoops. What is it doing here? It's going a bit mental. So here we have the specific directory. So this is the source code for this particular demo. So as I mentioned, we've got a example application, which is a looking image classification example. So given a picture of a dog or a cat, it's figuring out which one it is. So this is actually based off the lesson 1 of the Fast.ai course. And here is the example notebook. And here we essentially are not doing anything SageMaker specific. It's basically I've copied and pasted most of the same source code from the lesson 1 from the Fast.ai course, except for defining a few things here, such as where we're going to save the model artifacts. But essentially all of the code here is exactly the same as you're doing building any other Fast.ai algorithm with Jupyter notebooks. So nothing SageMaker specific. So here we've just got some code. It does image augmentation. We're finding the right learning rate. We're doing some learning rate annealing and freezing some of the layers. So these are all the kind of standard steps if you go through the Fast.ai course that you would do. So the only thing extra that we're doing essentially is here. So basically from this point on is sort of something SageMaker specific. So here we need to save the model. So this will save the weights of our convolutional network local to the local disk. And then what we're going to do is we're going to bundle that saved model up to S3. So this is where we can then use those model artifacts for machine learning model hosting. Cool. So that's the sort of the build. Really, that's all it is for the build and train phase. So now we're going to talk about how we can build the Docker image for our machine learning model inference, and then actually deploy that model as well as the image to the SageMaker hosting service. So as I mentioned earlier, typically once you've saved your model locally on SageMaker, you probably want to shut down your notebook instance, because especially if you're running, for example, a P3 or a P2, that's going to be the costs are going to add up. So the rest of the exercise, we're actually going to work with Cloud9, which is the cloud-hosted IDE. So we're going to actually build the Docker image used for our inference code here. And we're actually going to use the same instance to actually call our endpoint. So I don't know if you can see. It's a little bit murky there. Can you guys see anything there, or is it pretty? You can? I'll try and blow it up a little bit. Let's see if. A bit hard to see here. Is that better? Yeah? Okay, cool. So I just wanted to take you kind of through the source code initially of for our inference image. So here we have a folder called convnet. So this is where we're going to be essentially loading the save convolutional network and then calling it for predictions. So we've got a number of different files, and in most cases you can keep them. So for example, we have an Nginx configuration file. We have an WSGI file that's for Gunicorn. We have a serve file. So the only real one that you would need to customize is this predictor.py file. So this is essentially this one here. So this is just a pretty simple Flask application file. So what we're doing is we're loading up some of the Fastai libraries. We're referencing opt.ml, and then it'll be model. So that's where we're going to read our model artifacts from our Docker container. We have a singleton object. So this is actually the singleton object where we're going to actually load the model into memory from the model artifact. And then here we have a predict API call on that singleton object. So here's where we're going to actually call the model, do basically a forward pass through the convolutional network to get the predicted class. And here's where we need to implement those two RESTful API calls. So if you remember /ping, we need to implement. So that's going to be what SageMaker is going to call to verify that our inference image is working fine. So here we're just essentially loading up the model, and if it loads successfully without any errors, we're just going to return a success code. And then we have the invocations. So this is going to be where the clients are going to call. So they're going to upload our image to the service via a post request. So what this application is going to do is it's going to take that raw sort of JPEG image data, it's going to save it locally as a JPEG file, and then it's going to call the predict method on that singleton class. And then it's going to return two values, essentially in a JSON object, sorry. It's going to return the predicted class, so whether it's a dog or a cat, and also a confidence score in our return code. So that's kind of really all it is to the actual source code for your inference image. So now I'm going to quickly show you as well the Docker file. So this is the Docker file for our inference image. So what we have here is it's just a standard Ubuntu Docker image. We're going to install mini-conda, so that's to set up our conda environment. We're going to clone the Fast.ai library here. And here we're going to create an environment for Fastai. Now, there's one change here, because if you remember what I mentioned earlier, is we're actually going to run the inference image not within GPU, but actually on CPU architecture using the compute-optimized instances. So that means we don't need a lot of the libraries like the CUDA libraries and GPU-specific libraries. So thankfully, in Fast.ai, there's a separate environment file which is just specific for CPU that we can use. So we install some, the Flask, Unicorn packages from Python, and then we copy basically all that source code over into our inference image. So that's basically us ready to go. So the cool thing is with Cloud9 is we can run all our Docker build commands. So I actually have a script here. So I've got a little script. All it does is runs the Docker build, and it's going to actually push that Docker image that's built locally on a Cloud9 instance up into my private Docker repository in ECR. And obviously done it faster because otherwise, it's multiple gigabytes, would take minutes to do. So it's already cached locally and it's already been pushed up. But just to kind of show you the sort of the flow. So here is now the Docker image that we're going to use for inference. So what we can do is we can copy this. And now we're ready to essentially create our model and deploy it using the SageMaker hosting service. So what we can do is we can come back to our web console. Now, a lot of the following commands you can all do through, for example, the SDK or other means, but just for demonstration purposes, I'm going to show it in the web console. So the first thing we need to do, so now that we have built our model artifacts and we've built our Docker image for inference, now we can create a model in the SageMaker console. So that's as simple as coming in here, creating a model, giving it a name. So here we specify a role. So this will be the role given to the infrastructure that's going to use for hosting. So if you need to access S3, so the minimum is sort of accessing those model artifacts in S3 and also being able to pull down your image, your inference image from ECR. You can run your hosting infrastructure in a particular VPC. And here's the key ones that we're going to fill in. So we're going to put in, we're going to put in the name of our Docker image and upload it to ECR. And we're also going to put in the model artifacts here to create our model. So here we can go back to, where are we? Here. So this is our notebook. So we can copy essentially the model artifact that was uploaded when we've finished our training on the notebook instance. And we can just copy it in here. We can leave some of these others blank, and we can just go create model. So here we have our model created. And now we're ready to deploy the model to the hosting service. So we'll give it a name. Can create a new endpoint configuration. So this is where we're actually going to tell the endpoint what is the model we're going to use, and also define the infrastructure that we're going to use. So here we can define that we're going to use the compute-optimized instances, or we can define how many we want. So that's kind of dependent on sort of the throughput or the number of requests that are going to be called to your particular endpoint. So we can go London Summit. Fig. And here is where we add the model. So we've just created this model. And here, by default, it's giving us the M4X large and 1. So we can accept these defaults and create this endpoint config. And then here, if we click here, it'll basically go away and create the endpoint. Now, this will take a few minutes because it actually needs to, SageMaker is actually now going and provisioning those underlying instances that those instances will then pull down the Docker image, and then if the health checks are successful, then it'll put it in service. So I've created a endpoint before this demo, so we don't have to wait for that to be set up and run, which is the one here. So what we can do now, I can show you how we can actually now call that endpoint. See if it's working. So I've got a little script here. So it's a Python script that looks in the data directory. So if you see here, there's a data directory, and there's a test folder. So these are all test images of sort of a randomization of either dogs or cats that we want to classify. So we'll take a random image from that directory, and it will use the SDK, the Python SDK, to call my endpoint that I've configured. And I'm passing in, essentially, as a parameter, that endpoint name. So this is the existing endpoint that's up and running. And then hopefully it'll tell us, give us an accurate prediction. So let's see if it's working. So let's just see. So it's predicted to be a cat, so let's just see. Okay, so it's a cat, so that's working okay. So get another one. So it's just getting another random photo from that folder. So it's cat again, looking all right. See how we do here. What's this one? Cats. They're all cats. Let's see if we can try and get a dog. Here we go. It's a dog. Let's see if this is a dog. Yeah. So as you can see, it's working, which is great. So it's basically calling that endpoint. So you can basically call that endpoint from wherever you like. Great. So that's the end of the demo. It's been obviously pretty quick, but hopefully give you a flavor of what's possible and how you can bring essentially your own custom algorithms to Amazon SageMaker. What I'm going to do in the slides as well, put a link to, I've got a GitHub repo with the source code, so it includes all of the that ConvNet folder with the prediction source code, the Docker files, and also includes the Jupyter Notebook showing you how you can train your model and then push it up into S3. So we'll make that available so you can kind of look in detail and play around it with yourself. So thank you very much for attending. Enjoy the rest of the summit, the beers, and see you again soon. Thanks.